Hi everyone. This is just a little primer on some more details about moments of inertia, which you've already started to begin to use this table in a Torx dynamic, assignment. And so we talked a little bit about different shapes will have different moments of inertia depending upon how their mass is distributed. So just a little quick review of this idea. Any shape that's rotated about an axis has some little element of m. You could call it m sub I, some little piece of the object, a distance r sub I away of the rotational axis. And really, the moment of inertia, the total moment of inertia, you have to sum up all of those ith masses at their r distance away. And if you add all those up, that gives you the total moment of inertia for the object. It's a scalar quantity, so if you could count all those infinitesimal pieces at each of their distances away, you could use a computer to break up the object and add them all up. In this day and age, that's done a lot in engineering. But there are some simple shapes, and it's good to know how you could process those kind of from calculus to add up all of those ith pieces. So some of them, by symmetry, are pretty easy to understand. Remember that the definition of moment of inertia is r squared m, okay, for a mass. So for instance, if you just have a singular mass, right, m, or, at some distance r away, so this is not a rod, this is just the showing you that it's the distance r away from some point O, right, then for this mass out here, that distance r away, its moment of inertia about O is r squared m. All right, so a hoop is pretty easy to understand because all of its mass, a thin hoop, all of its mass is at a constant distance r away from the center. So its moment of inertia would be the same as for a point mass. It's just the mass of the hoop times its radius squared. Whereas if you have a disk, right, and some of the mass is closer in and some of the mass is farther out, the moment of inertia ends up being 1/2 mr squared. Okay, some more complicated shapes like a sphere. If it's a solid sphere, notice how this is shown to be colored in here. So if the whole thing was filled up like a bowling ball, then the moment of inertia is 2/5 mr squared. But if it's a thin hoop like or a thin sphere like a shell, like maybe a basketball, then it would be 2/3 mr squared. So this constant changes depending upon how the mass is distributed about the radius. Now the other most common one is a baton. So about the center, it's 1/12 ml squared. But if you try to shake it about the end, it's harder to shake a stick about the end because the mass is distributed a little further out. And so you can see that it's 1/3 ml squared. So we're going to take a look at how you come up with this one. And then we'll take a look at another. All right, so let's deal with the rod first. Okay, so if we take a look at calculating the moment of inertia of a thin rod about its origin at its midpoint, it's like twirling a baton about the center, or maybe a drumstick, and it's hard to start rotating it, given that it, giving it an angular acceleration with a net torque of your fingers, because it has mass and its mass is distributed about the origin at those different distances. So you can try to twirl your pencil and feel that. If you try to go about its center, right, and try to shake it, you can feel that it's harder to get moving and it's hard to stop to make a change and go the other direction. So that's what's meant by its rotational or its moment of inertia. That's different than just trying to make the pencil start going, right? That's just its regular linear inertia. Okay, so if we take a look at what we do here, we set up a coordinate system on the object like the baton. So the green object is like the pencil. We put the origin at the middle because that's where we're going to rotate it about that axis. And what we can think about is, due to some little element of mass out here somewhere on the rod, some distance r away, there'll be a little bit of the moment of inertia due to that little mass right there. So we could define that as di equals r squared dm. Now what we have to do is, because that mass is distributed all about the entire shape, is we have to add up all of those little dm's. So that's where the calculus goes in. So what we do, since our origin is here, we let our limits go from negative L over 2, right? That's half the rod. And this would be our, in our third and fourth quadrant. And it extends out to the first and second quadrant here, out to the length of the rod divided by 2. Then we get things in terms of the length of the rod. All right. So what we do is we kind of consider the rod as a one-dimensional object. Now, this is something where you might not have thought about this idea before, but in physics we do these things all the time. We make kind of approximations that allow us to come close to something, and then you can do, if it's not a thin rod, if it's a thick rod, then you'd have to treat things a little bit differently. But if you consider the rod or the stick as a one-dimensional object, you can define a density for the mass. Now, we have to do this because we need the mass as a function of its length if we're going to do some type of an integration of m here. So what we can define is if it's a uniform stick, right, so there's not more density at one part than the other part, we can define a density. Now, you guys are usually used to thinking about density as mass per unit volume. All right, you've done that before, so like grams per cubic centimeter and different things like that. But if it's a one-dimensional object, the stick could actually have a uniform mass per unit length density instead of a mass per unit volume density. So we can define that as it's like if you put a meter stick on a balance, if it's made out of wood, the meter stick's made out of wood, it would have a certain mass for its entire length. If it's made out of metal, you'd put it on the balance and it would have a different mass per unit length. So that mass density just tells you what the mass is over L. So the units would be like a kilogram per meter using our SI standard physics units. Or you could express the M as lambda times L, right? So you'd have kilograms per meter times meters, and any little portion of that stick, right, if you multiplied it by that, you would know, so 40 centimeters or 0.4 meters multiplied by that density, you would know how much 40 centimeters of the stick, what its mass was. Notice the lambda is not wavelength. I know we use that for waves, but different constants can be used in physics at different times, or not the constants, but different variables can be used at different times. And so just don't let that bother you. Okay, so the other thing we can realize that is if we shrink the portion of the mass down to some little dm element, right, and then we know that that same ratio dm over dl or dm over dr, kind of the same idea there, right, would also be that same constant density. So or up here, if you differentiated the mass, right, if you took dm dl, you would be left with lambda. So if you took a look at it from this point of view. So we're going to use that. Okay, now that's probably not apparent. That might not be something you would necessarily normally think of doing, but this is kind of how it's done in all of these cases. You have to come up with some mass expression as a function of r, some distance away from an origin. Okay, so dm is lambda dl or lambda dr, and we've got our limits, and so we know that our ith, or our di, is equal to r squared dm for some little portion of its moment of inertia out here about the origin again. Now we just set up our integral. So what we do is we're going to sum them all up, right? So what we can say is we can replace the r squared dm. So if we integrate right here, right, so what we're going to do is set up this integral here and this integral here. And what we can do is we can replace dm as a limit of our integral with something as a function of r. So we just said lambda, or dm can be expressed as lambda dl or lambda dr. And we'll put that right here. Okay, so that takes the place in this case. So this is a constant now. So this is why we can take the lambda out of the integrand, or realize that that we're not going to have to worry about that, and our limits of integration are going to be from negative L over 2 to positive L over 2. So we can see that this is a pretty easy integral. It's going to be r cubed over 3, evaluated from the plus L over 2 to minus L over 2, and remember our lambda is just going to be out front. So when we do that, we would have lambda times quantity L over 2 cubed divided by 3, minus negative L over 2 cubed divided by 3. And so from here on out, we've done the tough bit of the calculus, I guess, and the rest becomes algebra. So this becomes L cubed over 24, because 2 cubed is going to be 8. All right, and 8 times 3 in the denominator will be 24. You get the same thing again. 2 negatives make a positive. And this gives us the lambda times 1/12 L cubed. So now we can come back and remember that we said that lambda is m over L. So in terms of more macroscopic properties of the object, we can substitute back this expression back in for lambda as m over L. And we're going to end up with what we have here that you found in the table, that I for a rod about its center, okay, a thin rod about its center, is going to be 1/12 ml squared. So again, notice that that's a constant, right, times ml squared or mr squared. And then what we end up is that's that k. So that's how you can determine the k for an object. So now what you should do is you should do exactly the same integral to understand this, except what I'd like you to do is set up the integrand a little bit differently. So in this case, the other way you can twirl the rod is about the end of the pencil or about the end of something. And what you'll notice if you do this, right, is it's a little bit harder about the end than it is about the middle. So the question is, could you do the integral? And you should, as practice, and I just showed you how to set everything up for this. The only difference is if you're rotating it at about the end, the new limits of integration go from 0 to L. And if you do this, you should come up with what they have in the table, which is 1/3 ml squared. And knowing how to deal with this is the one that shows up sometimes on the AP exam. So knowing a real quick way to find the one for a thin rod, or at least understanding the basic process about it, is something that you should be able to do. So try that one, and if you can't come up with the 1/3 ml squared, let me know. Or there's lots of videos on the internet too that show you how to do it. All right, that's the basic idea.